In order to start talking about how temperature and pressure and things affect gases, we've got to make a few assumptions, and we're going to start talking about what's called kinetic molecular theory. Kinetic molecular theory talks about how gases move, right, and how they behave. So we've got to make a few assumptions, because when we talk about gases, we want to talk about what are considered ideal gases. And ideal gases are when gases behave exactly as we think they should, right? It's like when they follow all the rules. And typically gases behave ideally, right? I'm using that term in parentheses because ideal is the actual term, right? When gases behave ideally, it's typically at really standard temperatures and pressures, right? At very normal temperature ranges and very normal pressure ranges. If we get into scenarios that our temperature is really, really high or really low, and if our pressure is really high or really low, gases behave a little differently. They start acting a little bit different. And so for our purposes right now, we're going to make these assumptions to consider gases ideal, right? We want to deal with ideal gases. So these are 5 kind of parts to the kinetic theory that we need to think about. All right, in any gas, there are a large number of molecules, all moving in continuous, rapid, and random motion. So molecules move in a straight line until something else stops it, okay? Until it runs into, what other things could it run into, right? If I'm a gas particle and I'm moving in a straight line, what are other things that I could possibly run into? Yeah, the wall or the edge of the container, right? The wall of the container, whether that container is the room, whether that container is a flask or a bottle, right? What's something else I could run into?
Oxygen?
Yeah, like another gas particle. Yeah, so another one of those gas particles. I could run into those things. And so these particles they will move in a straight line until something else acts on it. That's Newton's first law, right? Newton's law of inertia says an object in motion will stay in motion. An object at rest will stay at rest unless something acts upon it. And so those gas particles are going to continue them. Molecules on average are very, very far apart from each other. When we were learning about protons and electrons in Chem 1 this year, Mr. Moritz did a demonstration to give us an idea of the scale of how much of an atom is really empty space. And we can make that assumption even larger for how far apart our molecules are, right? He said, if I'm in the nucleus of an atom and I'm standing right here at the corner of the school, then my electron would be like at Walmart, right? That's how far apart they are. So that means if we were talking about the space between gas molecules, if I'm a molecule and I'm standing here at the corner of my school, the next gas particle in my container might be like at Leavenworth, right? Or Kansas City or something. I mean, they are far apart, right? In relative to their size, they are extremely far apart. So that means most of a gas, what we consider a gas, is empty space, right? If we have a container that says this is 2 liters of helium gas, most of that in all reality is empty space, right? And there's gas particles moving around and floating around, but a lot of that is made up of empty space, okay? In an ideal gas, the attractive forces of a molecule that are in close proximity are ignored. So we know from our chapter on gravitational force that there is a gravitational force between any 2 objects, right? And it's never enough to outweigh the gravitational force between me and the Earth. But we know there's a force there. And in reality, in these particles, when they get close enough together, there's an attractive force that makes them hold on for just a second before they collide. But in ideal gases, we're going to assume that they make a perfectly elastic collision. There's no attractive force there. We're just going to assume that they collide and they come right back apart. Okay? So last thing, if we think that collisions are perfectly elastic, what does that mean is happening? Are they combining and sticking, or are they hitting and bouncing apart? They're bouncing apart, right? Elastic collisions is a collide and bounce, and an inelastic collision is collide and stick, right? We know that from our last chapter. In a perfectly elastic collision, we assume that all the kinetic energy is transferred from one atom to the other atom, or one molecule to the other molecule. So typically these gas molecules will be identical, right? H2 and H2, or Cl2, Cl2, right? And so they have equal mass. And so when those things collide, all of the kinetic energy from one is transferred to the other and vice versa, right? They swap velocities there. Okay, so those are some assumptions that we have to go under to be comfortable using what are called the gas laws. All right, so I'm going to give you several different equations here about gas laws. How many of you are familiar with the gas laws? Boyle's law, Charles' law, combined gas law. Have we heard of any of those? Or this will be all a little bit new to us? Heard of them a little bit, but maybe not super familiar. Okay, that's fine. So the first thing that we're going to start with is called Boyle's law. Boyle's law says that volume is inversely proportional to pressure at a constant temperature. So when our temperature stays constant, they are inversely proportional. And inversely proportional means if one goes up, the other goes down, right? So I want to walk through that here in just a little bit, but this is the equation you'll need for Boyle's law. P1 times V1 equals P2 times V2. Okay, I'll give you a second to get that written down, and then I'm going to walk through a few more things in this slide here. So let's look at this equation here. P is obviously our pressure value, and V is obviously our volume value. The 1 and the 2 just constitute pressure before some change, and then this side of the equation, the 2, represents after some change. So this equation allows us to see what happens to the pressure or the volume after a change is made. Okay, so let's imagine here that I've got just a balloon that's filled with gas particles, constant temperature, right? But let's imagine my balloon is sealed somehow, right? And I take my balloon and I kind of squeeze it up and I make the volume of the balloon smaller. What happens to the pressure inside that balloon?
It becomes hot.
The pressure is gonna go up, right? The pressure is gonna go up because now I've got a smaller amount of space for those particles to be. And pressure is really the measure of how much force is applied over an area, but pressure is essentially how often are those molecules hitting the walls of the container, right? So the smaller my container, the more often they are going to hit those walls. Does that kind of make sense? Likewise, if I were to make my balloon bigger, that would allow my molecules more space before it ran into a wall. So it would decrease my pressure. Okay, do you feel comfortable with that? Okay, here are the units. Pressure is typically measured in what's called atmospheres, and it's abbreviated with ATM. Okay, atmospheres is the most kind of common mathematical usage for pressure. It's not necessarily measured in atmospheres a lot, but we can convert to atmospheres a lot of different ways. So I'm gonna list those here for you. Okay, there are a lot of different ways that we can measure pressure. The first of which is called millimeters of mercury. So the conversion is 1 atmosphere of pressure is equal to 760 millimeters of mercury. So mm is millimeters. Hg is the atomic symbol for mercury. So millimeters of mercury is that pressure unit. Okay? It seems really odd, right? Why are we having a pressure unit that's a length, right? But that pressure unit comes from what's called a barometer. Do you know what a barometer is? A barometer measures atmospheric pressure. So it's literally just a small little wooden device, and it's got a column of mercury. So here's just like a wooden plate, and it's got a skinny little column of mercury here on it. Almost looks like a thermometer, right? But the column of mercury, however tall it is, right? The dark is the mercury inside. That might be 760 millimeters. This might be 750, right? And when the pressure in the atmosphere changes, it will shrink that column or raise that column, right? It's just within that little vessel, the mercury itself will essentially be pressurized or depressurized, and it will tell us that atmospheric pressure. So it's literally measuring how tall this column of mercury is, okay? So that's one of my pressure units. The other pressure unit I want to make sure we know is one that is typically used when we put in tire pressure or when we think about tire pressure. Does anybody know what that one is? PSI, good. Do you know what that stands for? Okay. PSI stands for pounds per square inch. So pounds of force per square inch. And the conversion is 14.7 PSI. Okay, and that's very much an American unit, right? For tire pressure or I don't know, pressure like that. But that's really an American unit. Okay. And then the last conversion I want to give you is the most scientific, I don't know how you say it, but 1 atmosphere is equal to 101.3 kilopascals. Okay, so the K stands for kilo, and then PA is for pascals. That is the pressure unit. Okay, kilopascals is most commonly the pressure unit that scientists measure pressure in. So experimentally, when they're doing different experiments, like the one we're going to do in the next couple of days, we're going to do a gas laws experiment. Our pressure sensors will measure in kilopascals, and then we can convert them to atmospheres to make our math simpler, right? To make our math more convenient. So those are the 3 main pressure units. There are a few more that I don't think we really need to have listed out there, but I would have those available to you so that if you have to convert, you could. Okay. Volume is mostly measured in liters. Okay. I will tell you that for this equation, we could keep milliliters on both sides, right? As long as it's consistent, right? If both of our volumes are measured in milliliters, you can keep them. But we need to at least make sure that we have consistency on both sides. Okay. Here's one extra conversion I give you down here. 1 meter cubed is equal to 1,000 liters. This would be like me finding the volume of a cube, right? Meters times meters times meters is meter cubed. I don't know about if you know this conversion either. 1 centimeter cubed. 1 cubic centimeter is equal to 1 milliliter. I don't know if you know that one or not, but that's the same thing, right? A milliliter is equal to cubic centimeter. So those are both volume units. Have you heard that term, that centimeters cubed? What about, have you heard the term cc's? Where does that sound familiar from? I need 50 cc's. Stat. Yeah, like in medical stuff. Okay, that's okay. I'm practically a doctor because I watched, a lot of seasons of Grey's Anatomy. So, anyway, so cc's is a medical term because isn't it simpler for me to say I need 50 cc's than I need to say I need 50 milliliters of that, right? It's cumbersome. So cc's is the unit for cubic centimeters, and it's equal to the milliliters. So it's the same thing. Okay, so that's a lot of information I gave you with that law. Do you want to do a practice problem with that one? You want to try one? I didn't write any on your slides, but I'll just write one out to the side if you want to write it underneath here. Okay, I'll just kind of make one up here. Let's say, what's the final pressure of a 1.4 liter balloon at 1.2 atmospheres that is compressed to 0.8 liters. Okay, so this says, what is the final pressure of a 1.4 liter balloon at 1.2 atmospheres that is compressed to 0.8 liters? Okay, so I think it's important here to kind of make our list of what variables we have. We're looking right here, it says final pressure. So that means I'm solving for P2, right? That has to be my question mark. It's asking me right up front, what is the final pressure? Okay, then it says I've got a 1.4 liter balloon at 1.2 atmospheres. Those two terms have to go together. So that means that's my V1 because it's liters, 1.4 liters, and my pressure initial or P1 is 1.2 atmospheres. It says it's compressed to 0.8 liters. So that has to be V2, 0.8 liters. So do you see you have to really use context clues to figure out which of my values are initial and which of my values are final. Would we agree with that? We really just have to use context clues very carefully. So we're going to read that very carefully. And then we just plug it in, right? P1 times V1 equals P2 times V2. Okay, so 1.2 times 1.4 divided by 0.8. Before we even finished the math, my volume went down. So what would we expect my pressure to do? Go down or go up? Go up, right? So we should expect our pressure to be greater than 1.2. And I ended up with a value of about 2.1. Is that what we had? Okay. So easy peasy, right? Gas laws, I think, are some of the easiest stuff we do. It's very much just kind of a list of equations, and we got to pick the right equation and then plug them in. Okay? Reading those problems carefully might be the trickiest part. All right, so let's look at the next one. Considered Charles' law. Charles' law now says the volume of a given gas is directly proportional to the temperature when the pressure is kept constant. So directly proportional means if one goes up, what does the other one do? It goes up, right? One goes up, the other goes up. For these gas laws, our temperature always, always, always has to be in Kelvin. Okay, and I'm going to show you why here in just a second, but our temperature has to be in Kelvin. Okay, here's just a graph of temperature versus volume, right? As one of them is increasing, the other one is increasing, right? So it looks nice and clean. But here is our equation for Charles' law. You'll notice here it says that pressure is kept constant. So pressure is left out of our equation altogether, right? We don't need pressure in our equation if it's kept constant because it's not changing on either side. Do you remember how to convert from Celsius to Kelvin? Right? This is just an addition conversion. And to get from Celsius to Kelvin, we're going to add 273. And that would equal my Kelvin temperature. Okay, so if you're not comfortable with that or you don't have that memorized, we need to go ahead and write that down because that's going to have to be something that we do a lot. With these problems, it's typical for us to be given our value in Celsius, and then we need to convert to Kelvin every single time. Do you have any thoughts as to why we must convert to Kelvin? Why can't we keep it in Celsius? If we just look at the equation here. Any thoughts on that? What if my temperature was 0 degrees Celsius? Can I put a 0 in the denominator of a fraction? No, right? So that's one just pure mathematical reason why I can't keep things in Celsius. So I always, always, always have to have my temperature in Kelvin. And that's true for all of the gas laws. Okay, for every gas law. Okay? I'm not going to, do we need to go through a problem here or do we feel pretty comfortable with how that works? Yeah? Let me actually just spend 1 second here. I'm going to give you just the variables. I'm not going to write out a word problem. But I'm going to say if V1 is equal to 16 liters, T1 is equal to 294 Kelvin, V2 is equal to 19,000 milliliters, what's T2 equal to? Okay, do you see any red flags here? Liters and milliliters are inconsistent, right? I need them to have the same unit. And so I want to go ahead and just convert that to liters, right? Do you remember how to convert milli to liters? Divide by 1,000. So we're going to divide by 1,000, which means we're going to Move that over, so that means we really have a volume of 19 liters. Okay? Now, knowing what we know about the relationship between volume and temperature, my volume increased. So what would I expect my temperature to do? Increase. These ones are directly related. That's okay. Directly related, which means if one goes up, the other goes up. Okay, so let's go ahead and plug in here. V1 over T1 equals V2 over T2. Now, do we know how to do the math on proportions like this? I'm going to cross multiply and divide. So I multiply, cross multiply, then divide. Is that term familiar to you? Cross multiply and divide. So I'm going to take 294 times 19 divided by 16, right? So I'll take 294 times 19 divided by 16, and I get a final temperature value of 349.1 Kelvin. Okay, and so did that meet our expectation of going up? Yeah. Okay, so are we comfortable with the math that goes in there? Okay, very good. All right, let's look to the next one. Our next one is called Gay-Lussac's law. And this is where we see a relationship between pressure and temperature. Pressure and temperature. So in this case, volume would be kept constant. These two are directly related as well, and it looks very similar to Charles' law, except we swap out pressure and volume. Okay, so now we've got P1 over T1 equals P2 over T2. We've got a graph there again that shows the direct relationship between pressure and temperature. Okay, I don't think I need to plug in a practice problem here because it's going to look very similar to the one we just did. But again, our units for pressure need to at least be consistent on both sides of our equation. And what does my temperature need to be in? It has to be Kelvin all the time. Has to be Kelvin. Okay. What would happen if they asked me to solve the problem, but then they asked me to report my final temperature in Celsius? How would I get from Kelvin to Celsius? Perfect. Yep. All I would have to do is subtract 273, right? I'm just going to reverse that we did earlier. Very good. Okay. All right. Let's move on to, now we're going to smush them all together, right? We're going to take Boyle's law, Charles' law, Gay-Lussac's law, and smush them all together into what's called the combined gas law. We're going to combine them. Okay. The combined gas law is P1 times V1 over T1 equals P2 V2 over T2. So you see how this is just all three of them put together, right? Boyle's law is that. Charles' law is that. And Gay-Lussac's law is that, right? We just smush them all together. So in all reality, I could just memorize this one and I'd be able to use it for every scenario. And I just know if pressure was constant, I'd just leave it out, right? Or if volume was constant, I'd leave it out. So if I know the combined gas law, I therefore then know all three of the other ones. Okay? I don't know if I have a problem built in here. I don't. But let's go ahead and try a problem here. I'm going to write up one again, but I will tell you that with the combined gas law, it's more difficult to predict if my temperature is going to go up or my pressure is going to go down or whatever, because there's two things that are affecting it now, right? You've got to look at the relationship between pressure and volume and how it affects temperature. So these are a little bit more difficult to predict our final outcome here. So you just have to be confident with your math and what that would look like, okay? All right, so I'm just going to write up a problem here. Let's say a 70-liter balloon at 2.4 atmospheres and 300 Kelvin floats higher to a new pressure of 6.3 atmosphere and a temp of 240 Kelvin. What is the final volume? Right, so we've got this balloon. It floats higher in the atmosphere, which is increasing our pressure and decreasing our temperature. And we want to know what's the final volume of my balloon. Okay, so let's just start picking out, let's start picking out what information we do have. Okay, 70-liter balloon. There's our volume, pressure, and temperature. Are those the initials or the final? 70-liter balloon at 2.4, 300. These are all initial, right? So I'm going to go ahead and just start plugging them into this equation. Okay, so P1 is 2.4, V1 is 70, and T1 is 300. Okay. It says it floats higher to a new pressure of 6.3, so that's P2. I'm looking for final volume, so that's going to be V2. And then my final temperature is 240. Okay, so now we've got a situation in which our unknown is left here. So it's not like a super simple and clear cross multiply and divide, but I still am going to start with that principle. I'm going to cross multiply and divide. So I'm going to do that step first. So let's go ahead and do that. 240 times 70 times 2.4. And then I'll hit enter, right? That's my multiply. And then I'm going to divide that by what? 300. And so by doing that, I now am left with 134.4 equals 6.3 times V2. And so what do I need to do to get V2 by itself? I need to divide that by 6.3, divide by 6.3, which gives me a V2 equal to about 21.3 liters. Right? So we are actually cross multiply, divide, and then you can divide by your secondary number right there if that's comfortable for you, right? So in my calculator, I would have done 240 times 70 times 2.4, enter. Divide by 300, divide by 6.3. That way I can do it in just one quicker step. I mean, we're talking about saving one number punch, but that's about it. Okay, mathematically, does that part make sense? Okay, we multiplied by 240 to move it over, right? That's what happens in our cross multiply. Okay, very good. All right, the last gas law that we are going to focus on is called the ideal gas law, right? And the ideal gas law combines temperature, pressure, and volume and the amount of moles of our gas present. Has it been a long time since you've heard the word mole, right? A mole of gas. Okay, let's take a step back here real quick and think about what a mole is, right? Chemistry-wise, what a mole is. 1 mole of anything is equal to 6.022 times 10 to the 23rd of that thing. Okay. Does that number ring a bell? That's called Avogadro's number, right? 6.022 times 10 to the 23rd. So 1 mole is equal to that many molecules of any kind of gas. Okay. So if I had 2 moles of gas, I would take that number times 2, right? If I had 6 moles of gas, I'd take that number times 3, and that would be how many molecules I have. Okay. Is that ringing bells from chemistry, hopefully? Okay. All right, so this, I'm sorry. The difference with the ideal gas law compared to all the ones we've done so far is that the ideal gas law does not have a before and an after. There's no change that happens when we use the ideal gas law. The ideal gas law just says, if the temperature is this and the pressure is this and the volume is this, how many moles of my gas do I have? That's really all that they're asking. Or if I have this much gas at this pressure, what's the temperature in that situation? So there's no before and after. That's how you know which law you need to use. Okay, so here's our equation for ideal gas law. PV equals nRT. We definitely recognize P, V, and T, but N and R are new there. Okay. N represents the number of moles, and R is what's called our universal gas constant. Universal gas constant. And this is a number that you'll memorize or have written down. Excuse me. But this number, 0.0821, will always go into the ideal gas law. So the one thing that we need to pay attention to is that in order for R to work, these are the units. R's units are liters times atmospheres over moles times Kelvin. So that means in order for R to work, our volume has to be measured in liters, pressure has to be measured in atmospheres, moles, and temperature has to be measured in Kelvin. Okay, so for this ideal gas law, we can't let the volume stay in milliliters, and we can't let the pressure stay in PSI. We have to convert them to liters and to atmospheres. Okay? All right. So I've given you tons of information. We haven't done a lot of practice with them yet, but we've given you a lot of information. The last thing I want to talk about before we get into the practice is something called STP. STP stands for standard temperature and pressure. So STP is a set of conditions, a set of pressure and temperature conditions. So it might say a gas has a volume of 50 liters at STP. And if it says that at STP, that means that in that set, my temperature is 273 Kelvin and my pressure is 1 atmosphere. So anytime it says STP, you already know the pressure and you already know the temperature. Okay, you already know the pressure and you already know the temperature. 273 and 1 atmosphere is considered STP, standard temperature and pressure. Okay, this says, what is the volume of 1 mole of any gas at STP? So I'm not telling you which equation to use. We have to try to figure out which of our gas laws we have to use here. What is the volume of 1 mole of any gas at STP? Any guesses as to what law we should use? Boyle's, Charles, Gay-Lussac's, combined, or ideal?
Ideal.
I think it has to be ideal. Good. And why would we say that? That's right. It's the only one that has moles, right? So that would make a difference. So it's asking me for the volume. I know my moles is 1.0. But what do I know about STP? I already know my pressure and my temperature. So at STP, what's my pressure? 1 atmosphere, and my temperature is 273 Kelvin, right? I know that because we gave you information about STP. So we're going to use the ideal gas law. PV equals nRT. Pressure is 1 atmosphere. Volume is my unknown. Moles is 1. R is always 0.0821. And my temperature, we said, was 273. So it's really just plug it in. So I'm going to multiply everything together on my side without the variable. Because, right, these are all multiply variables. So I'm going to take 1 times 0.0821 times 273. That gives me 22.4 equals 1 atmosphere times V. So do I need to bother with the dividing the 1? Is it going to change my number? No, right? So my volume there equals 22.4 liters. Okay, and so that's true for every gas. That's actually called Avogadro's principle. He said that no matter the gas, every single type of gas at STP, 1 mole of it has a volume of 22.4 liters. Okay, sometimes we use that number in chemistry as a conversion factor, similar to how we use grams or Avogadro's number. Okay, all right, let's try the next one here. Actually, I want to skip to this one, and then I want to come back to that last one, because that middle one is pretty tricky. So I want to do a little bit simpler one first, and then we'll come back. Okay, a car tire is filled to a pressure of 1.97 atmospheres at a temperature of 10 degrees Celsius. After driving a while, the temperature of the tires becomes 40 degrees Celsius. What is the new pressure in the tire? Okay, so I've got information about a pressure, a temperature, and a pressure. So what equation can we use? No, Boyle's law has which two? Pressure and volume. But I want pressure and temperature. So I need to use Guy-Lussac's law, right? P1 over T1 equals P2 over T2. Okay. So here's my pressure, 1.97 atmospheres at 10 degrees Celsius. 1.97. Can I keep it at 10? Can I just say it's 10 degrees? I need to convert that. 10 degrees Celsius plus 273 would give me my Kelvin. So that would become 283 Kelvin. Okay, I'm solving for my new pressure, but my final volume is 40. So I'm going to go 40 degrees Celsius plus 273. Gives me what? 313? 313 Kelvin. And so now we cross multiply and divide. Right? My temperature increased. So I would also expect my pressure to increase. And in our case, I think we did, right? I got about 2.18 atmospheres. This question is asking us for grams of helium. Do we have any of our equations that call for grams? No. So what's the closest thing we can come to that? Or what's the thing that we can use to help us get to grams? Any ideas? Okay, we're going to have to end up solving the ideal gas law for the number of moles of my substance of helium, and then I can convert to grams. Okay, it's probably been a long time since you've had to do that, convert moles to grams. That's a chemistry topic, right? But it's something that we've done before, right? If you're in this class, I'm assuming you've taken chemistry, so something we've done at some point. So that means my goal is to first solve for moles. Okay, so that's going to be what my question mark is for right now. My pressure is 1.05 atmospheres. So if I want to use the ideal gas law, can my pressure be in atmospheres? Yeah, that's what I wanted it. I do want my pressure in atmospheres. It says my temperature is 20 degrees Celsius, so I don't want to keep it in Celsius. I'm going to add 273 to that, and I get a temperature of 293 Kelvin. I always know what R is, so I don't need to write that out, but my volume here is where it's going to get a little bit tricky. It tells me my volume of my perfect sphere. It actually doesn't tell you my volume. It tells you the radius of my sphere. So I came on here and gave you the equation for volume of a sphere. Okay? And so here's my thought process. Here's how I would go about it. I'm going to go ahead and keep my radius in centimeters, because I know centimeters cubed is equal to 1 milliliter, and then I can easily convert that to liters. Okay, you could convert meters first and go meters cubed to liters if you wanted to, because I gave you that conversion also. So it really makes no difference, but I'm going to go ahead and just keep it in centimeters for right now. So let's go ahead and solve for the volume. 4/3 times pi times r cubed. Okay, 4/3 pi r cubed. So I'm going to take 18 cubed times pi times 4/3. Right, that's the volume of a sphere. So when I did that, I don't know, tell me what you got. That's about what I had, 24,429. Is that similar to what you guys had? Okay. So that's in centimeters cubed, which means we also know that that's equal to the number of milliliters, right? Because 1 centimeter cubed is equal to a milliliter. And so now if I want to convert, I need to get it to liters. I can say 1,000 milliliters is equal to 1 liter. And I'm just going to divide that number by 1,000. And I get a volume equal to 24.4 liters. Okay, do we feel comfortable being able to go through that? I know that was a lot of just cumbersome, right? We had to go through a lot of steps to get there. But does every one of those steps seem to make sense? Okay. So now I'm going to come over here and I'm going to plug in 24.4. And now I get to use the ideal gas law. So P times V equals N, right? I'm solving for the number of moles, times R times T. Okay, so I'm going to multiply, this whole side and this whole side, and we'll see what we get. In my calculator, I would do 24.4 times 105, and then I would hit enter, and then I would do divide by 0.0821, then divide by 293, right? Because I want to move both of these to the other side. So divide by 0.0821, divide by 293, and I get a number of moles equal to about 1.06 moles. 1.07 maybe if we need to round that. Are we staying with me so far? We're close to the end, but we're not quite there yet, right? It called for not moles, but grams. So we've got to do one final conversion, and this is a pure chemistry conversion. So this is pure chemistry knowledge. If I want to convert moles of helium to grams of helium, moles of helium goes on the bottom, grams of helium goes on the top. Okay, and I know that 1 mole of helium is equal to the molar mass in grams. So for helium, it would be 4 grams, right? Molar mass is the smaller number that's in the corner. The atomic number is in the left-hand corner. So the bottom right corner is the atomic mass or the molar mass. And so I know that moles gets the 1. And there are 4 grams of helium for every mole of helium. And so now I just multiply across the whole top, divide by the whole bottom, and I get 4.26 grams of helium.